So good afternoon, everyone. Welcome to the final review, review 4 out of 4. So this is going to be the last hour and a half of review that we will have. So I hope that you found that this class was interesting. I hope you learned a lot. I mean, based on what we talked about the other day, I feel like looking back, I was like, wow, we actually covered quite a lot of stuff. So that's good, and on the other hand, it means that there's a lot of topics to remember for the final. So I want to make sure that you're best prepared as possible. So with that, any questions? Yeah.
2.4 number 11, it was like graphing functions, but I think the way that they like said to do it involved polynomial long division, and I couldn't remember if we did it that way or not.
Okay, let me take a look. You said 2.4, right? Yeah. Part A or part B? Okay, part A. Preview. Question 11. Is this the right one?
Yes.
Okay. So okay, this one, yes. So graph as a transformation of 1 over x. And the function is g of x equals to negative 4x minus plus 1, sorry, and then divided by x plus 4. Okay, so let me make it so you can see. All right. So we want to make a graph of this function. Now, what you kind of need to already understand before you even try to graph this as a transformation of 1 over x is what does the graph of 1 over x look like? Because then we're going to move it left, right, up, down, twist it, whatever, right? So the graph of 1 over x has a vertical asymptote at what x value? What x value is going to give us an asymptote for 1 over x?
Negative 4.
Well, just for this function.
Oh.
Just for 1 over x.
0.
Yeah, just x equals 0 will give us an asymptote. So we know that we have some kind of weird behavior going on near the line x equals to 0, which is a vertical line. And you can check whether it looks like this, or if it looks like this, or whether it looks like this, or whether it looks like this. How can I check which one is the correct graph of 1 over x if I forgot what it looks like? So what we want to take care of is this whole fraction will have the same sign as whatever is the sign of the denominator. If the denominator is negative, the fraction will be negative. If the denominator is positive, then the fraction will be positive. Another way you can think of this is to say, look, the limit as x goes to 0 from the left, you take x values which are close to 0 but negative. That means this number will be 1, and the bottom will be like something negative and very small, which will produce a number which is very negative and big. Okay, if you divide by a small number, that's the same as multiplying by a big number. So this tells us we look like so. We look like so on the left-hand side, okay? On the right-hand side, you're going to see the opposite. So this is minus infinity, whereas the limit as we approach from the right is plus infinity. And if you want a review of how we do these sorts of limits, okay, you can go back to the Tuesday office hours review session. There's some more in detail idea of how we do these limits. Okay, but loosely speaking, this tells us that we have up on the right side and down on the left side. So we are going to view this as a transformation of 1 over x. The only problem is I've got multiplication. I have x in the top and in the bottom. So this is not just a transformation of 1 over x. I can't get to this by just adding and subtracting and multiplying by numbers. I've also got an x in the numerator. So in order to graph this as a transformation of 1 over x, we're going to need to manipulate this expression a little bit. And the way we're going to do it is using long division like we talked about in class earlier today. So we want to divide negative 4x plus 1. We want to divide out x plus 4. And let's see what happens when we get that. I think we just get negative 4, and then we would subtract negative 4x plus, actually not plus, but minus, negative 4x minus 16, right? So then the 4x, negative 4x cancels with negative 4x. We subtract negative 16. We get 17. Okay, we get 17. So the answer of this division is negative 4 plus 17 divided by negative 4x plus 1. Okay, negative 4x plus 1. No, what am I doing? I was like, that's not right. This should be the x plus 4, right? Because that's what we're dividing by. Okay, so we have a whole number plus a remainder. And now this looks like a transformation of 1 over x. What is it going to do if I go from 1 over x is my parent function. This is my child function, if you want. What is subtracting by 4 going to do to the graph? Shift down 4 units. What about adding 4 underneath?
To the left 4?
Yeah. So this is going to be a horizontal shift because you can view the parentheses as being like right here. Okay, so adding in the parentheses is going to cause us to move to the left 4. And one more thing. We talked about these two already. What's left? Yeah, the 17 is going to do something. It's going to stretch us. How? Vertically or horizontally? It's going to be vertically. It would be horizontally if it was down here in the denominator. Okay, so here's what we have. We have a horizontal shift. Left 4. We have a vertical stretch. Factor of 17. And we have a vertical shift. Down 4. Okay, so if I was going to make the graph of this, I'm just going to move this all to the left 4 and then down 4, and then I'm going to accentuate this and make it more sharp, basically, if you want. So maybe some, oops, not like that, but like this. And then I would draw like this line, I'd say is y equals negative 4. And then this line, I'd probably say is x equals negative 4. Left 4, down 4, yes.
Which 4 shifts it to the left and which 4 shifts it down?
Okay, so you just came in. So what we're doing is talking about this problem, which is a transformation of 1 over x, where we view this as a transformation. We did long division, and we got an expression like this. Can you help Chris understand which one represents a shift down by 4, and which one represents a shift to the left by 4?
The down is the negative 4 on the outside,
Mm-hmm.
and the left 4 is inside the parentheses.
Okay, good. So Sully got it exactly right. It's the one on the outside of the parentheses. So it's a little confusing because you're used to seeing a vertical shift like on the back. But you could rewrite this whole equation as 17 over x plus 4 minus 4. like that. This maybe is in the more familiar shape to you in terms of when you see something like being added or subtracted and it's on the outside like that, then we are in the up and down world. If we have a multiplication or an addition on the inside, then that's the side to side world. Okay? Good question. Any other questions on this one? Okay, then any other questions? Next problem?
Can you go over how to find the domain and range and the I guess we know the horizontal.
Sure, yeah, we can do that. We can do, why don't we do domain, range, horizontal asymptotes, vertical asymptotes, all of that. Let's just graph, actually. Let's graph. I promised we would do one of these eventually, didn't I? Let me try to get all of the different types of things that there are. Okay. So for graphing, we had like 6 things or something like that. Six steps. Okay, let me show you what I want to see in your picture. I want y-intercept. I want zeros. And correct behavior. By correct behavior, I mean passing through the x-axis or bouncing off of it. I want vertical asymptotes. And behavior. I want horizontal asymptotes. And behavior. Or, if no asymptotes, end behavior. Is that it? Vertical asymptotes, horizontal asymptotes. Y-intercept, zeros, behavior, behavior. Have I missed anything? Let me go back and check and make sure. This was chapter 2, right? Here's chapter 2. Chapter 1. Am I losing my brain? There it is. Jeez, I don't know why it's so far down there. Let's see if I can find the 6-step thing. Here we go. Okay, so intercepts, vertical asymptotes, horizontal asymptotes. Oh, okay, symmetry. I don't really care about symmetry. I mean, you can include symmetry if you want. But definitely horizontal asymptotes. Oh yeah, and then any holes also.
Do we have a question about
Symmetry for a rational function. I mean, I could ask you a question like, is this function even or odd? Right? But I'm not going to ask you, like, is this function symmetric about this axis or that axis? But yeah, I might ask you if a function's even or odd, which has to do with symmetry. I don't think there's many questions on the homework that ask about symmetry, are there? So, yeah, probably not. Okay, so these are all of the things that we want to do. So let's start with your question, which was about the domain of this function. So if this is f of x, Let's talk about the domain of f of x. Well, the domain of any function is the set of inputs which are allowed to be plugged in. And there's a couple inputs which I can't do for this function. The main thing I want to look for when I'm doing the domain is I can't do square roots of negative numbers. I can't divide by 0. And I also can't do like a log of a negative number, okay? So these are the three things that I have to look for when I'm doing domain. No logs of negatives, no square roots of negatives, no dividing by 0. Which one of those is going to be a problem for us in this problem? Alexa?
What if these, well, I want to say square roots of negative.
Okay.
Or 1 over 0.
It's 1 over 0. That is definitely going to be a problem. And actually, we don't need to worry about square roots, simply because I don't see any square roots in the numerator or the denominator, so we should be pretty safe from that. And likewise, I don't see any logarithms, so probably don't need to worry about that. But we do have a fraction, which means we do have to worry about possibly dividing by 0, right? So that's going to happen in basically the two scenarios, right? We have 2 times x squared times x minus 1. There's two numbers that could cause this equation to be 0. What are they? If you plug them in for x. Yeah, 1. 1 would cause this number to be 0. What would cause this number to be 0? What number could you plug in? Yeah, just 0. So for a rational function, finding the domain is as simple as that. It's just finding when is the denominator going to be 0, right? So if you wanted to describe it using interval notation, you could say negative infinity up to 0, union 0 up to 1, union 1 up to infinity. Because you just want to throw out those two numbers. We don't want 1 and we don't want 0. So we throw them out. So two different ways to write the domain. And actually, not only are these values not in the domain of the function, they're also going to cause us to have some really wacky behavior. Because when the denominator gets really close to 0, this function is going to be doing crazy things, right? Kind of like how 1 over x does something crazy. When the denominator gets close to 0, we see these like asymptote type things happening, right? So we're going to see something similar going on for our function. So in fact, we can say that we are going to have a horizontal, not a horizontal, but a vertical asymptote. The first one is going to be when x is equal to 1. Now, to determine the behavior at 1, you can do one of two things. You can manually compute limit x goes to 1 from the left of f of x, and a limit as x goes to 1 from the right of f of x. See what happens when you plug in a number like 0.99, or see what happens when you plug in a number like 1.001, okay, something like that. So try that. That's one option. The other option is to use the theory. The theory says, look, the multiplicity of this 0 in the denominator is 1, okay, power 1 here, as opposed to x equals 0 is going to have multiplicity 2. So the multiplicity is 1. That tells me I have opposite behavior on each side. And then I also need to check what is the sign of the leftovers, which by the leftovers I mean what I get when I plug in. I'm going to forget about the 0 that I'm worried about, and I'm going to check what is the sign when I plug in 1 here and 1 here and 1 here. That would give me 4 times -1 squared divided by 1, which would be 4, which is larger than 0. Okay? This means I am going to have behavior which looks just like 1 over x. Okay? Because this looks like, this behavior is going to be like four over x minus 1. And this is just a transformation of 1 over x. This is 1 over x shifted to the right 1 unit and vertically stretched by a factor of 4. Okay, so let me go through that again. I know that I'm going to have one of these two type behaviors. I'm going to have either this one or I'm going to have this one. The reason that I know that, okay, with like these being our asymptotes and this being like this, okay, the reason I know it's going to look like one of these two is because the multiplicity of the 0 in the denominator is odd. Okay, the multiplicity is odd.
How is it?
So the multiplicity refers to the power. So you see how like
Oh, yeah.
here I've got 1, power 1, and here's power 1, and here's power 2 and power 2. Those refer to the multiplicity of each 0. So x equals -3 is a 0 of multiplicity 1 of the numerator. X equals 2 is a 0 of multiplicity 2 in the numerator. And whether the multiplicity is even or odd is going to tell us whether we have like same behavior on both sides, okay, so namely like one of these two type things, or whether I'm going to have opposite behavior on each side, which would be like one of these or like one of these. Okay, so the two with the same behavior on both sides, that goes with even multiplicity, even like 2, 4, 6, 8, and then the ones that are opposite means odd multiplicity. So I just need to pick which one it's going to be. And whether it's going to look like this and this, or whether it's going to look like this and this, depends on the sign of this number, which is what you get when you plug the 0 into the rest of this thing. Okay, so I call these the leftovers, by which I'm referring to everything except for the 0 here. Okay, everything except for that 0, that's my leftovers. You plug in the 0, check the sign of that number. That tells you what is the behavior going to be like in terms of that. So basically the behavior will look like if you just replace all of this crap by 4 and you leave x minus 1 in the denominator, that will be like the behavior that you're going to see there. So this is only local behavior, like very close to our 0 or our asymptote. So what do we know so far? We know so far that, let me use this page to do a really big graph. Let me spread things out nicely. So we know we're having a vertical asymptote at 0 and at 1, right? So let me draw those in. Here's x equals 0, and then here is x equals to 1. What we know is our function close to x equals 1 will present itself kind of like this, which this function looks just like 1 over x but moved over a little bit. So it in particular is going to be down on, oops, let me go back to regular mode. It is going to be down on this side and then question mark, because that's too far away. And it's going to be up on the other side, and then we don't know what it's going to look like after that. But we know that very close to x equals 1, it will look kind of like the graph of this function. Any questions so far? I gotta bust out the Red Bull. This problem is gonna take me like an hour.
Are you choosing the questions from our homework thing?
As opposed to making my own? Or?
Like how we did like the previous exams? Like
Yeah, the exam questions will come directly from the homework. Yeah. but a problem like this is on your homework, so it's worth going over. Okay, let's have another one. So what have we done so far? We've done the vertical asymptote for x equals 1. Now let's do the vertical asymptote for x equals 0. For x equals 0, the multiplicity is 2, which is even, which means we're going to have same behavior on both sides. Same behavior. Next up, let's do the leftovers. The leftovers is what I'm going to get when I take this expression and I plug it in. I'm going to forget about this 0 this time. I'm going to forget about this term for now. And I'm going to see what I get when I plug in 0 here, and 0 here, and 0 here. Then I would get 0 plus 3 times 0 minus 2 squared divided by negative 1, which is 3 times 4 is 12, divided by negative 1 is negative 12, which is less than 0, which means the behavior nearby will look like this number, negative 12, divided by 2x squared, which is kind of like negative 12, negative 6 over x squared. Okay, so you know that the denominator is a positive number, right? Which is going to 0. And the numerator is a negative number, which means that this is going to look like this type of a situation, okay? Because it has to go to infinity, either minus infinity or plus infinity, and it's a negative number, so you know it has to be going down to negative infinity. So now I know the behavior of the function near 0 is going to look something like this. Okay? And then again, question marks to fill in. Okay, so this is the oops. Yeah. So that's the vertical asymptotes taken care of. What else do we have to do? Let's go to the zeros next. Okay, so I'm going to need to copy this equation down again. Zeros. When is this fraction going to be 0? Yeah, the way that a fraction can be 0 is only if the numerator is 0. So you can forget about the bottom and just take zeros are going to be when the numerator, which is x plus 3, times x minus 2 squared is equal to 0. So there are two zeros. The first 0 is x equals to negative 3 with multiplicity 1. And the second 0 is x equals to 2 with multiplicity 2. Okay, multiplicity 2. So we know that the function is going to pass through the x-axis at these two x values, negative 3 and 2. So let me put them on here. So negative 3 is like somewhere over here. It's going to pass through the x-axis. Here's x equals negative 3. We know that it's going to go through, so probably it's going to connect something like that, if I had to guess. And then also at 2. So at 2, x equals 2. So probably it's going to pass through something like this, okay? Something like that. Something seems wrong here. Something has to be wrong here. Something's definitely wrong here. What is wrong? Oh, no, it's fine. But we know that, okay, yes, so we're fine. It's going to touch the x-axis at this point, but actually it's probably going to bounce because the multiplicity of this 0 is 2. If the multiplicity of the 0 is even, we're going to bounce off. If the multiplicity of the 0 is odd, as is the case for x equals negative 3, we're going to pass through. So actually we know a little bit more. We know it's probably going to look something like this here. And it's probably going to look something like this here, okay? So at the end of the day, our goal is to like draw this kind of connect the dot type of graph and then fill it in. So only a couple things left to do. That's the 0, and the behavior near the zeros is just going to be either bouncing or passing depending on whether it has even multiplicity or odd multiplicity. So next up is to talk about what? Oh, y-intercept. How do I find the y-intercept? How do I find the y-intercept of any function?
Set the thing equal to.
Fill in the x's for 0.
Yeah, Chris has got it. I think you might have been on the track to find the x-intercepts, Liv. We can find the x-intercepts if we take this whole thing and set it equal to 0. That's what we just did. To find the y-intercepts, we're actually going to plug in 0 for x, because the y-intercept is where this thing touches the y-axis, which is right here. All of the points on the y-axis have x value equal to 0. So we can find what is the height of the function when we plug in the x value 0. That'll tell us what is the y-intercept. Does that make sense? Okay, so let's do it. So if we do that, we would get... What would we get? If we put a 0 here, a 0 here, a 0... Uh-oh. A 0 here and a 0 here. What's going to happen? Numerator will be like 12. Denominator will be 0. But that's okay, because you know what? We just don't have a y-intercept for this problem. The reason we don't have a y-intercept is because x equals 0 is not in the domain. Okay, so there's no point on this because it's an asymptote. Okay, so no y-intercept for this case. So that's that. And what else do we have to do? We did the zeros. We did the vertical asymptotes. There's no holes. Why are there no holes for this one? When do I have a hole?
Isn't that one like, it's a number in the numerator and denominator like equal to each other?
Yeah, exactly. It happens when I have a common factor from the numerator and denominator. So if this was like x minus 3, okay, and it was like x plus 3 and x plus 3 in the top and on the bottom, you would cancel and cancel, but you would still have a hole there, okay? So no holes. Last step is to do the horizontal asymptotes. What determines whether or not I'm going to have a horizontal asymptote? And if so, how do I figure out what that horizontal asymptote is? Well, if I set the denominator equal to 0, that'll tell me when I have the vertical asymptotes. But we already did that. Numerator equal to 0 tells us whether we have zeros or where we have zeros. So that takes care of those two. So it's not numerator equal to 0. It's not denominator equal to 0. What do I need to check to find horizontal asymptotes? Yeah, the power of the numerator versus the power of the denominator, or the degree is the word we use, right? What is the degree of the numerator here? This is a polynomial of degree what? So actually what you would want to do is like FOIL this out, right? So this looks like x plus 3 times x minus 2 times x minus 2, right? So you would FOIL and then FOIL, and what you would get is the leading term will look like x cubed. From multiplying this guy times this guy times this guy, it'll be an x cubed. Okay, so the shortcut method is to add up all these numbers, okay? Add up all of the multiplicities of the zeros in the numerator. So this one has degree 3, and this one has degree 3. The degrees are the same. This means we are going to have a horizontal asymptote. If the degree of the numerator is bigger than the degree of the denominator, no asymptote. If degree of the denominator is bigger than the degree of the numerator, then what's going to happen? We are going to have an asymptote at what value? Loosely speaking, what does this mean? When x is really, really big, the denominator will be much, much bigger than the numerator. What kind of number is that going to produce? If the denominator is way bigger than the numerator, that number is getting close to what? 0. So asymptote at y equals 0. And if they're equal, then what? We're going to have a horizontal asymptote, but it's not going to be 0. It's going to be somewhere else. How do I figure it out? Well, if we were to multiply this out, it would look something like x cubed plus some other stuff. And in the denominator, it would look like 2x cubed plus some other stuff. And the only thing that matters for the end behavior is these two terms. I'm going to do something with them. Well, actually, I'm just going to forget all of the other stuff, and I'm just going to divide them. So if I divide them, so you divide leading terms, which for us means we are going to take x cubed divided by 2x cubed, which gives us 1/2 equals y as an asymptote. Okay? So let's do it. 1/2. So 1/2 maybe looks something like this. Except, let me change the style. Let's do it with yellow and dashed. And that is y equals 2. So we have all of the asymptotes. We know where it crosses the x-axis. So in particular, we know that it can't do something like, it can't connect like so. The reason it can't connect like so is because otherwise these 2 points would be zeros, but they're not. So I know it's going to stay underneath for its whole time here, which means I'm pretty confident in connecting it something like this. Okay, I'm pretty confident connecting it like that. Likewise, on the left-hand side, I know it has to go down here, and I know it has to eventually connect through here and go up to this asymptote, right? Which means I'm pretty confident it's going to go like this, and then it's going to go like this. Okay? And then on the other side, what's going to happen? I know it can't go through the x-axis, and I know that these two have to somehow connect in a smooth way, so I'd say it looks probably something like that. And then I know it eventually has to equilibrate up to y equals, not 2, this is 1/2. It has to eventually equilibrate like, ooh, not like that, but like this. Okay, so this is the 1 million step process of how to graph a rational function. So, this is something we learned over the course of many, many days, and we just took it piece by piece, okay? So when you look at this in terms of like a problem, it seems like there's so much to do. But each individual piece is not too bad. I think probably the hardest part is determining the behavior near the vertical asymptotes, if I had to pick a hardest part. Because there you have to check the multiplicity. You have to remember what kind of multiplicities give you same behavior versus opposite behavior. You gotta also take a look at the sign of the leftovers and determine whether it's gonna look, like this, or like this, or like this, or like this. So it's kind of a lot there. But if you go back to our notes, I gave you a handy guide somewhere. Here it is. This was the handy guide of how you check what kind of behavior you're going to get. So this is the type of thing that wouldn't be a bad idea to include on your formula sheet. And this is also on the Blackboard page.
Which, lesson is this under?
Sorry?
Which, lesson?
This is chapter 2, and this is section 2.4, I think. Yeah, all of these notes are on Blackboard, including the notes that I'm writing right now. I'm going to post them onto Blackboard. So you can look at them there if you want to steal some of my stuff to include on your formula sheet.
What is the Q for?
Q? Q is, okay. So if your original expression is n over d, okay, then the leftovers is like everything except for the 0 that you're looking at. You know what I'm talking about? Okay, so Q is just the letter that I used, or that the book used, to describe the remaining components of the denominator that aren't the 0. Does that answer your question? Okay. So, as you can see, this problem is really involved. It's totally fair for me to ask you about any of these topics, but I probably won't ask you to do something like this, like what I just did, like use the 6-step thing to graph this function. I would either ask it in terms of like a multiple choice, or I might ask you, like, what are the vertical asymptotes of this rational function? What is the horizontal asymptote of this function? Does it have any zeros? Things like that, like piecemeal. Okay, I'm not going to make you do all of this because this is too time consuming to do it all. But I wanted to have an example which demonstrated kind of all of the different types of behavior that you can see this thing do. So hopefully this will be a complete guide. And if you know how to do all of this, you'll definitely know how to do any of the sub-questions. Okay? All right, any final questions on rational functions? Yeah.
Not for rational functions, but can we do the rational root?
Sure, rational root test. I'll do that in just a second. Before we do that, though, I just want to ask if there's any lingering questions about all of the rational expressions. Yeah?
What did you say the lesson was that the notes were under?
It's chapter 2 is what it'll be. Like, I have this entire, like, note is like, I don't know, 45 pages long. And it's in section 2.4, so it's towards the end of the chapter 2 notes if you want to look at it. Or if you want to look at the book and see an even better diagram than this. Actually, I don't know if they have this diagram in the book. But yeah, you can look at my notes. They're posted onto Blackboard as a PDF, and you can find this in the chapter 2 notes. Other questions? Yeah.
Are there any specific formulas for this section that you should know?
This one I'd probably recommend knowing. You mean like for more?
Like for chapter 2.
For all of chapter 2. Yeah, let me look through. I mean, this would be a good thing to put on your formula sheet as well, regarding like whether you have horizontal asymptotes or not. What else? Okay, so before that it was just division. I would put the rational root test, the rational root theorem or whatever, on your formula sheet. I don't know, you could put the quadratic formula on there. But I think probably a lot of you have that memorized already, so maybe not. Yeah, those are like probably the main like formulas that I would pick out of this chapter. Does that help? Okay, any other questions on rational functions before we do a rational root test thing? . Okay, then let's do a rational root test problem. And this is the problem we're going to do. I have no idea if this is going to be hard or not. Well, maybe I can find a better one. Okay, this is a better one to show you this. So we did this one in class, but I'm going to assume that if I've pretty much forgotten it, you probably have forgotten it too. So let's try to factor this function using the rational root test. So let me copy down what the rational root test says. Here's the rational root test. Copy. Paste. I'm going to make it smaller and put it over to the side. Okay, so we want to factor this function here. And as you can see, it's a cubic function, which we can't just go ahead and like use factoring as we would ordinarily with like a quadratic, right? We can't use grouping. Maybe there's a way to group it, but generally our recourse with the cubic polynomials is to try to guess a factor, then divide it out, then factor or quadratic formula the resulting, what will I get if I divide this by a linear factor? What will be on top? If I divide a cubic by a linear, what kind of result? A quadratic. The power will be reduced by 1. So I will use factor or quadratic formula on the resulting quadratic equation or quadratic expression. Okay? So this is our goal. So the rational root test comes in with step number 1. So step number 1, we want to guess one of the factors of this thing. So sometimes you can just look at it and you can kind of see. With this one, I don't think I can really see easily what the factors of this thing are or what is going to make this 0. Like you can try to visualize like what would happen if I plugged in 1. That'd be like 3 minus 2 minus 6 plus 4. 3 minus 2 would be negative 1. Minus 6 would be minus 7 plus 4. Okay, so 1's not a 0. What about negative 1? Then you can try negative 1 and try some other ones. You can sometimes get lucky by guessing, but sometimes it's hard to see what the zeros could be. So it's useful to have a short list, and that is what the rational root theorem allows us to do, is to develop a short list for the roots. So it's been a while since we did this, but this is the general form of a polynomial, okay? an and an minus 1 and a1 and a0, they're all numbers. And they're attached to the various powers of x. Okay, the various powers of x. So the very first term is called the leading term. And specifically, the an, the number which is attached, is called the leading coefficient. And the last one is sometimes called like the constant coefficient or constant term or the tail term. In other words, okay? So what they're telling us is that, look, if you have a 0, which is like p divided by q, it's a rational number. So think numbers like 1/2 or 3/4, or 1, or 3, right? 3 can be written as 3 divided by 1, and so on and so forth. You all right?
Yeah.
Okay, just making sure. Yeah, no, I had like a 20-minute coughing fit yesterday because I inhaled some water, so I'm right there with you. Okay, so P over Q is a rational number if the numerator and denominator are whole numbers, okay? So could have the denominator equal to 1, in which case the 0 will be like a whole number. Or if the denominator is something else, you could have like some kind of fraction. But the point is, if you have a rational number, which if you plug it in gets you 0, then these two things have to be true. Namely, the numerator has to be a factor of the tail, and the denominator has to be a factor of the leading coefficient. Okay, so here's how we apply it in this problem. We know that if P over Q is a 0, then P is a factor of 4, the final term. So P will be a factor of A0, which is the constant term, which for our problem is 4. And Q is a factor of 3. Okay, Q will be a factor of 3. So let's see what kind of numbers we can make. So if P is a factor of 4, that means it's going to be in like, it's going to be a number like 1 or 2 or 4. Those are the factors, right? And what are the factors of 3?
3, 1.
Yeah, just 3 and 1. So we know that we can make a bunch of numbers here. We can make a bunch of numbers, okay? So what does it say? The theorem says if P over Q is a 0, then this is true, which means that P over Q will be one of the following. So this means is included in the set, and here's the set. Plus minus 4, plus minus 2, plus minus 1, plus minus, so those were when the denominator was 1, and the numerator was 1 of 1, 2, or 4. And then the other ones will be when the denominator is 3, and the numerator will be 1 of 1, 2, or 4. So that gives us 1/3, 2/3, and 4/3. Okay, so now we have a list of plausible zeros. Okay, plausible zeros. Let me think for a second. Okay, so yes, at this stage, you can find some or all of them. If you want to plug everything in, you can find all the zeros, and then you just have it factored. But it's kind of annoying to plug them all in. What's easier is if you can find one, then you can divide it out and solve the remaining quadratic. So I would probably start by plugging in like 1 and -1, and then I would move on to like 2 and 4, and if I still haven't found one, then I'd be like, okay, fine, I'll plug in some of these fractions, right? So probably the one that I would find first would be x equals to -1. I think that one will work. Let's plug it in. We get 3 times -1 cubed, minus 2 times -1 squared, minus 6 times -1, and then plus 4. Let's see, is that going to give us 0? This is -3, minus 2, plus 6, plus 4. No, that's not going to give us 0. What am I doing? That one's not going to work. Sorry. Let's see, maybe 2 will work, or minus 2 or something like that. Okay, I'm just going to cheat and tell you that x equals 2/3 works. Okay, and let me show you. It would be 3 times 8 over 27 minus 2 times 4 over 9 minus 6 times 2 over 3 plus 4. When you do this, you get 8 over 9 minus 8 over 9 minus 4 plus 4 is equal to 0. Cancel, 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 cancel. You get 0. But what would you do? On the exam, well, first of all, I probably wouldn't give you one with fractional things. I'd give you a shorter list so that you would have more time to check them all. But anyways, you just check them one by one and plug them in and see if you get 0. Once you have one that does give you 0, we've guessed the factor, okay? If x equals 2/3 is a 0, implies that x minus 2/3 is a factor, which means that when I do the division, when I divide x minus 2/3 out of 3x cubed minus 2x squared minus 6x plus 4, I know that since it's a factor, this is going to divide out nice and evenly, okay? Nice and evenly. So let's do it. How do I do this long division? What should go here? 3x squared. Good. Minus, and I do what I get when I do 3x squared times this and times this. That's what goes in here. So I get 3x cubed minus 6. No, what am I doing? Minus, let's see, multiply 3x squared times 2/3, we get 2x squared, right? Okay, so we get lucky. Cancel, 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 cancel. We've got negative 6x plus 4. So what else is going to go in? What comes next? Yeah, I need to do negative 6 so that negative 6 multiplied with x will give us negative 6x. So we subtract negative 6x plus 4, and hey, it worked out nicely. And we're left with the following. So this is all to say that 3x cubed minus 2x squared minus 6x plus 4 can be rewritten as the product of x minus 2/3 times 3x squared minus 6. Okay? Because this thing divided by x minus 2/3, if you divide both sides by x minus 2/3, you get what we just did from the long division. Is that clear? Any questions so far?
So you got like you scroll up.
Mm-hmm. Yeah. Yes.
The 3 and then like the 8. I mean, in the parentheses like 8 and 27. You just plugged in 2/3 slash the original expression.
Yes. You're talking about here?
Yeah.
Yeah, so what I did was I took 2/3, plugged it in here and here and here. Yep. I just did that math in my head. So 2 cubed is 8, 3 cubed is 27. That's how I got 8 over 27, and so on and so forth. You good with that now?
Yeah. You said like on the exam you would probably use like 4.
Yeah, I'll probably give you nicer numbers than this. Okay, so I'm not quite done yet because my goal was to completely factor this thing, but it's not completely factored yet. Okay, it's not completely factored yet. I can do a little more factoring. I can factor this, right? I can write this as x minus 2/3. I can take a 3 out, so 3 out front, and then I'm left with x squared minus 2, right? So I can factor it a little bit more. 3 times x minus 2/3, and this is a difference of two numbers. So its factors are going to be x minus the square root of 2 and x plus the square root of 2. Okay? Yep.
How are we able to bring the 3 out front? If it's not in the x minus 2/3.
So this has a 3 and this has a 3 in it. So I pull those out here. I divide both of those two terms by 3.
I mean like the one, like x minus 2/3.
Over here?
Yeah.
Well, okay, so I actually brought the 3 out to here. And then you can do multiplication in any order.
Okay.
So I moved it to the front.
Okay.
Because x times y times z is the same as y times x times z.
Oh, so it's just like its own individual thing.
Yeah,
Okay.
exactly. Yep, it's its own individual thing. So if you wanted to be like very complete, you could write an intermediate step where you say x minus 2/3 times 3 times x squared minus 2, like that. And then I just like to put numbers at the front, so that's why I moved it over there.
So would it matter if we had 3 in front of x squared minus 2?
Would it matter if you had it here? No, that's fine. That's fine. If you want to keep it here and you had 3 here and not here, that's fine. No worries. Yep. I just think it's easier to it's friendlier to the eye, as it were, to look at it like that, in my opinion. Okay, so that's a rational root test problem. Next topic.
I'm not sure what unit it's from, but we had like a question on the quiz that was like determine if this is even on or neither, and there's like 2 formulas that go with it.
Yeah, okay. Let's practice determining whether or not a function is even or odd or neither. I think that was chapter 1. Like 1.7 maybe? Oh, that's 1.9, so we need to go earlier. Maybe it was 1.5. Okay, average rate of change, that's another one I would put on your formula sheet. This one here. And here we go, even and oddness. Okay, so let's go through the definitions and then we'll take a look at how to check. So a function is even if it is symmetric about the y-axis, which what that really means is that, look, if you take an input x, okay, and you take the opposite of that input, okay, so these are the 2 inputs that I'm talking about, are x and negative x, which can be seen here and here. Then, if it's symmetric, the height of these 2 points should be the same. Okay? So we have opposite inputs, but same output. That's what even means. Okay, so for example, f of x equals x squared. Why? Because if you do negative x, quantity squared, guess what you get? If you multiply it out, you multiply negative x times negative x, what does that give you? Just x squared again. Okay? So if you take the negative of the input, you get the same output as if you had just plugged in the positive of that output. Okay, so namely like negative 2 squared is the same as 2 squared. Negative 3 squared is the same as 3 squared. But it's not enough to just say that, look, negative 2 squared equals 2 squared, done. That's not enough, because you could have a function for which that's true, right? You could have a function which looks like this. You know, it could look something like this. Okay? This function goes through this point and this point, but it's definitely not symmetric, right? This is not symmetric. So just checking one point isn't enough. We have to check all of the points, which means we have to do this in generality, okay? We need to do this in generality. So let's see how we do it in generality quickly after I show you what is the definition of an odd function, which is to say if I have opposite input, the output will be opposite. So you could put the negative sign here if you want, or you can put the negative sign here if you want instead. Okay, however you want to write it. All I want is that if the input is on the right side and we move it over to the left side, the output should be the negative of whatever it was before. Okay, should be the negative of whatever it was before. So namely, this distance is a number, and this distance is that number but negative. Right? So, for example, x cubed. Why is x cubed symmetric about the origin, i.e. odd? Because what do I get when I do negative x cubed? you get a negative times a negative times a negative, which gives you a negative. These two numbers, namely x cubed and negative x cubed, they're opposite, right? No matter what x is. Okay, so how do we determine whether a function is even, odd, or neither? We just check for evenness. We plug in x and we plug in negative x and we see if we get the same thing. So let's try it with this one. I'll delete this. And I'll go through this one. So let's try with x cubed minus 4x. I want to check whether it's even. If it is even, then this will be true. So I want to know if this is true. That's why I put a question mark here. So let's see what the left-hand side is. The left-hand side is just x cubed minus 4x, right? And on the right-hand side, I'm going to plug in negative x with parentheses. I will get negative x cubed minus 4 times negative x. Left-hand side stays the same. Let's simplify the right-hand side. It would become negative x cubed plus 4x. So they're not the same. Okay, they're not the same. Does that make sense? So that's how I can say with confidence this function is not even. When I plug in negative x and I plug in x, I don't get the same thing on both sides. Let's check oddness. Well, what do we want to check if we do oddness? We want to check if f of x is the same thing as negative f of negative x. Okay, so let me show you again how this works. F of x, remember, is x cubed, what is it, minus 4x? Minus 4x. I want to check, is it equal to negative f of negative x? So here I'm going to put in f of negative x, which is negative x quantity cubed minus 4 times negative x. And now let's just multiply out the right side a little bit. You get negative x quantity cubed minus plus 4x. And then I'm going to distribute this minus sign onto both of these. When I do that, what am I going to get? The negative will become a positive, x cubed, and the positive 4x will become a negative 4x. And would you look at that? These two things are the same. Since they are the same, and that's the definition, it's basically to say, look, if this equality is valid, then the function is odd. We said, look, this equality is the same as this, is the same as this, is the same as this, and this one is true. So we follow the line of inference backwards and say, well, therefore this is true, and this is true, and this is true, and therefore the function is odd. Does that make sense? Okay, so checking even and oddness, by the way, this is another one that I would put on your formula sheet, is look, even function, I would write even f of x equals f of negative x. And I'd write something like plug to check. You know, you see what I'm saying here? And then odd, f of negative x equals negative f. Oops, f of x equals negative f of negative x. Plug to check. You know, give yourself little notes and stuff like that to help you remember what you're supposed to do, in addition to, you know, whatever the formulas are. Okay? So that's even and odd functions. Does that answer your question? Okay. And there's some that you should have memorized are even or odd. Like, for example, numbers or functions like x to the p. If p is even, the function is even. Like x squared, x to the fourth, x to the sixth. If p is odd, the function is odd. X cubed, x5, x to the seventh. Other ones that you should have memorized in terms of even and oddness, sine and cosine. Which one is odd? Sine is odd. You can tell by looking at the graph of sine. The graph of sine looks like this, right? This is symmetric about the origin. Symmetric about the origin means odd. So this is the graph of sine. Sine is odd. The graph of cosine, on the other hand, looks like a mustache. And mustaches, as long as you have a good one, are symmetric, right? Okay. So that's cosine. I don't know. You could have like a really crazy, like one-sided mustache. I don't know if I've ever seen someone pull that off, though. Anyways, you get the point. That's even or oddness. Any more questions on even or oddness? All right. Then next topic.
I just have another question on the rational root theorem. So on the last we did like that last expression that we wrote it as, is that so I did the homework once earlier and I wrote the answers as like I set them equal to 0 and then wrote it as that. Is that how we need to know what we should write it as on the exam? Because I think I might have been confused with what it was asking me to do.
Mm-hmm. Okay, well, let's look at this one. For this one, the directions were factor.
Okay.
So for this one, what I want to write ultimately is this is a cubic polynomial. In order to write it in its factored form, I need to write something like this, where inside of each of these is a linear term. If the question was instead said something like find the zeros,
Yeah, that's what it was. Or all
find the
possible.
zeros, or find all the possible rational zeros. If it was find all the possible rational zeros, then this would be your answer. If the question was find all rational zeros, then just x equals 2/3 would be your answer, because there are two other zeros, but they're not rational, right? Or if the question was find all zeros, then you would say x equals 2/3, x equals plus or minus square root of 2. You see what I mean? So it really depends on what the instructions say. If the instructions say find the set of all possible rational zeros, then you need to write all of them down like this. If the instructions say find all rational zeros, you need to check each and every one of these, or else solve for the rational zeros using some other method. In which case, only one of these zeros is actually rational, so this would be your answer. Or if it says find all of the zeros, then you would include all three of the zeros. Or if it says factor, then we're going to write it like this. Okay? Does that clear things up now?
Yeah.
Okay. Yeah, sometimes the instructions are a little bit different, so you got to be careful about reading the instructions, and you also got to look out for whether it says simplify completely. If it says simplify completely, then you got to go all the way to, no square roots in the denominator. You have to reduce 4/6 to 2/3, stuff like that. Okay, more questions? Or more topics? Yeah.
Okay, this is in general. Are the word questions at the beginning, obviously the intro stuff is important, but the ones about the boxes and stuff and the fences, should we know how to do those?
Yeah. Yeah, I mean, you should know how to do all of the problems. But yes, generally, I'm not going to say that there are word problems, and I'm not going to say that there aren't word problems, but I would say that you need to feel confident applying your skills to a word problem. You want to do one?
Sure.
Okay. Let's see. There was a good one in probably the quadratic homework. I think it was the quadratic homework. Does this one have the fence problem? Oh, there was a really good one about the box where you fold it or something.
I did not like that one.
That one was fun. Okay, come on. Projectile, this is basically you just look at this equation and you ask yourself, what's it asking? It's what's the maximum height? This is a quadratic function. It's just the vertex, right?
It's these ones I like.
See what I mean?
Yeah.
Or when does the projectile hit the ground? That's when the height is 0. So you set this equation equal to 0 and solve for t, right? Stuff like that. But for this one's a little bit more complicated. These ones are trickier, so let's try it. So this is homework 2.1. one, number 16. 340 meters of fence. And we enclose a rectangular region and one side doesn't need fence. Find maximum area. Okay, let me try to walk you through what goes through my mind when I have a problem like this, okay? Because it takes a while to build up your sort of skills in translating a word problem into a mathematical problem that you can solve, right? Because you're used to just being given the mathematical problem and you know how to solve it, right? But this is in some sense more applicable to your daily life than are other equations that you know how to solve. Okay, so here's how I walk through this. The very first thing is, look, if this is something that I can draw a picture of, you bet your bottom dollar I'm drawing a picture of it. Okay, so here's our river. And then we have some fencing, which looks like this. This is what I'm getting out of the problem. They say it's 3 sides of fence and then the river, right? And we want to make this area as big as possible. But the question is, how should I set up the fence? The question is, how should I set up the fence? Do I set it up like this, or should I use all my fencing to make a really long side on this side, and then just kind of shorter here, and then really long like this, right? I could do it like that. Or I could make it really, really long in the sideways direction, and really short, like that. So all sorts of different ways that I could enclose this area, but only one way, which is going to give me the maximum area. So let me erase the other two, because those are not reasonable. But here's what I need to do. I need to assign variables to this drawing, basically. Some natural ones would be maybe like x and y. Okay? The reason I like x and y are, or you could do y and x, whatever. Why don't I do x and y? Because x should go left and right, and y will go here. Okay? X and right will go. Okay. So then what are the governing things which are going to determine how this works? First of all, I know that the area is going to be given by what? Yes, something meters squared. That'll be the units. But if I know the side lengths, how do I figure out what the area is? Yeah, length times width, where length is x and width is y. So area will be equal to x times y. And there's one other equation which I also have. Which is going to have something to do with this number. Yeah?
Perimeter?
Yes, perimeter. How do I get the perimeter of this fence?
This one, 2y plus x.
Yes. So how much fence do I use? I use y meters of it here, and then I do another x meters of it here, and then I do an additional y meters of it here. So the total amount of fence which I use is 2 times however long the sides are, plus 1 times however long the top part is. 2y plus x equals to 340, because I'm going to use all of my fence. So these are my two equations, right? And now your goal is to find x and y which maximize the area, okay? So what you want to do is maximize the area, but this is an equation in 2 variables. How to maximize it is not clear, right? But there is a relationship between the variables that you're using. Namely, 2y plus x is equal to 340, which means that you can actually solve for how much fence is used here in the following way. The amount of fence which I use here is going to be my original amount of fence minus however much I use on the sides. See what I mean? that clear? So however much fence I use on the sides, I have 340 minus that much left over. So you can get this by just rearranging this equation, 340 minus y. And now I have two equations and two unknowns. We did something like this morning. What's the method we use?
Wait, why'd you get rid of the -2?
Oops, sorry, -2. Thank you. So two equations in two unknowns. How do I figure out what one of those numbers
Plug
should
in
be?
X.
Yeah, we're gonna plug in this for x here, right? So let's do it. Area is going to be equal to 340 minus 2y times y. Which could also be rewritten, I'm gonna switch colors back to yellow, which could be rewritten as 340y minus 2y squared is equal to the area. Okay, why was that useful? Because my goal is to find out the maximum of this function. And I'm in luck, because what kind of function is this? About a square. So functions with variables being squared. What kind of word does that remind us of? Starts with a Q. Quadratic. Okay, but why is that interesting? Because I'm supposed to find the maximum value of this. This is a quadratic, which the graph of a quadratic is a parabola. Which direction does this parabola open? Down. Which means this function looks like this. And I'm trying to find the maximum, right? Where's the maximum of a parabola at? The vertex. If it opens down, right? If it opens down, the maximum will be at the vertex. So let's solve for the vertex. Well, you can rewrite this as 170 y. I don't know. Let me not do that. Let me just say, you can rewrite this as negative 2y squared plus 340y plus 0. And the vertex will be at negative b over 2a comma f of, or rather a of negative b over 2a. So negative b over 2a is negative 340 over negative 2a is 4, so, or negative 4, excuse me. The negatives cancel one another out, and we get 170 over 2, which is the same as 85, right? Is that right? 85 times 2 would be 170, times 2 would be 340, so yes. 85, and then a of 85, whatever that is. How do I figure out what a of 85 is? You plug it in here. So that would be like, you know, negative 2 times 85 squared plus 340 times 85. Whatever that number is. Okay, so this whole problem has multiple steps. The very first step is, of course, to draw a picture, okay? This helps you to visualize it. From here, assign, you know, various variables to the, like, measurements of interest. For this problem, the measurements of interest are going to be the length and the width, because it's a rectangle, right? And you can notice that, look, the width on one side is the same as the width on the other side. From here, you can make your equations. You should have one for the thing you're trying to measure, and one other equation which comes from a constraint that you have in the problem. Namely, you have only so much fence. then you can use the constraint to cancel out one of the variables in your function to achieve a function in one variable. And once you have a function in one variable, as long as it's a quadratic, you can go ahead and easily maximize or minimize this, because the minimum or the maximum of a quadratic will always be at the vertex, depending on whether the quadratic opens up or whether it opens down. Okay, it determines whether you have a min or a max. The only other thing we used here was that the vertex of a quadratic is always at negative b over 2a. That's always the x value, and then the y value will be whatever you get when you plug it in to the quadratic function. So from here, in order to find the maximum, we determined, look, this is a parabola opening down. Therefore, it has a maximum. It will be at the vertex, and the vertex is here. So again, this question could have multiple different ways of phrasing it. In this case, it's find the maximum area, which means you want to give out whatever this number is at the end, right? Whatever is the maximum area that you can get. But another way this question could have been phrased is find the dimensions of the fence, which give you the largest area, right? And then you would be able to say, well, look, having the 85 be this width, you would want 85 here and you'd want 85 here, and you would use this equation to determine out what should the other dimension be, right? Does that make sense? Okay, so that's a word problem. At the end of the day, it's just applying the knowledge that we have regarding quadratics in a sort of a novel setup, right? But at the end of the day, if I give you something like this and ask you, what kind of shape does this graph make, you would probably be able to tell me parabola, and you'd probably be able to tell me that it opens down. And if I said find the vertex, you'd probably be able to find the vertex. So all of these tasks are sort of within your grasp. It's just that you have to know when and why to do them. That's what's hard about word problems, I think. Okay, but there's not that many word problems on the homework. You can probably cover your bases. All right, how much time we got left? 3 minutes. One more problem? Just for old time's sake? I don't know. Let's see, what else is there? Polynomial, zeros, logarithms, log rules, exponentials. Let's do an inverse trig. Five pi over 9.
Yeah, that was
That one's crazy. Why is 5 pi over 9? Did you have this on your homework? I might have removed this.
no, we did.
You did?
Yeah, I remember that
The
one.
hell? So 5 pi over... Oh, yeah, you can do this. You know what? You can use the spatial reasoning to do this one. Wow, that's kind of a hard problem. Well, no, I guess it's not that bad, but it's confusing at first. What is 5 pi over 9? That's like a little more than pi over 2, right? So it's somewhere like here-ish. This is 5 pi over 9. Thank you. Arc cos of 5 pi over 9. So 5 pi over 9 is somewhere here. So what we're looking for is a point on the unit circle whose x value is this x value, right? We want this x value here. Wait, excuse me? Arc cos of 5 pi over 9? Okay, now I understand why this is so messed up. What is 5 pi over 9? It's like, this is like doing arc cos of like 15 point something. No, like 16 point something over 9. Point something over 9. Why can I not do this?
It's above 2 pi.
It's that the input of the arc cos function is not an angle. The input of the cosine function is an angle. The output of the cosine function is the height of a point. And there are no points whose height is this number, because this number is definitely bigger than 1. So you're looking for a point on the unit circle whose height is like 16 point something over 9. And this is like asking the question, find the angle inside the unit circle which points at a point with this height. Well, there are no points in the unit circle who have that height. Man, that one even tricked me. That's crazy. I was so confused. I was like, why is this like this? Okay. Well, last question for the day. Stumped your teacher. It's too hard. All right. Well, if you come across any other questions in your studying over the weekend or something like that, then feel free to email me. If I have a minute, I can try to send you some notes back on any problems that you want notes on. And yeah, happy studying. I'll see you all on Tuesday, bright and early for the exam. You all are going to do great. And yeah, have a good one.